Lesson 11, Part 2. Type of structure: granular and cohesive. Granular. Soil particles are arranged in small, rounded units, common in surface soils on A horizons. Most distinct in soils with relatively high organic matter content. This is an example of granular content. The amount of water in a soil has a profound effect on its engineering properties, and for example, under compaction, dry density varies with water content. A soil compacted dry will reach a certain dry density. If compacted again with the same compacted effort but with water, a higher dry density will be reached. The water helps to lubricate the soil. The particles move closer on compaction. Also, air in the mixture is removed during the process. However, too much water reduces the density, and optimum moisture content occurs when the compacted dry density is at its maximum. And about cohesive, soil particles are arranged in plate-like sheets, which are approximately horizontal in the soil and may occur in either the surface or subsoil. Also, they are most common in the subsoil. Plate structure strongly limits downwards movement of water, air, roots, and may result from compaction. The range of moisture content over which the soil remains in the plastic condition is defined as the plasticity index and is calculated from the formula. Plastic limits equals liquid limit minus plastic limit. About density. Soil density. Density is the ratio in a mass of a material compared to its volume. Density equals mass divided by volume, which can be written as this formula, and the units are milligram divided by cubic meter. Bulk density represents the in situ density of the soil at a current moment in time, contain some water and air in the pores. Bulk density equals total mass divided by total volume. Dry density is when water has been removed from the soil. Dry density equals mass of solids equals divided by total volume. Or where this is as a moisture content and is expressed as a decimal in this equation. Saturated density is when the weight of the water is included in the weight of the soil. Saturated density equals saturated mass divided by total volume. When the volume of soil is submerged below the water table, you can see, it displaces an equal volume of water so that its effective or submerged density is density saturated minus density of water. And please note, mass is when gravity is not included. Weight includes gravity. Therefore, a soil's unit weight equals density multiply gravity, where gravity is equal to 9.81 meters in minus 2. For example, bulk density multiply gravity equals bulk unit weight. Dry density multiply gravity equals dry unit weight. Saturated density multiply gravity equals saturated unit weight. Submerged unit weight equals saturated unit weight minus density of water. If the density of fresh water is multiplied by gravity, the unit weight of water is obtained. That 9.81 kilonewton per minus cubic meter. Note the density of seawater is 1.025 milligram by divided by meter minus cubic meter, or 1.025 kilogram divided by cubic meter. Soil porosity. Soil porosity or pore space is the volume percentage of the total soil that is not occupied by solid particles. More space, pore space is commonly expressed as a percentage. Percentage of pore space equals 100 minus bulk density divided by particle density multiply 100, where bulk density is the dry mass of soil solids per unit volume of soils. Particle density is the density of soil solids, which is assumed to be constant. The particle density of a material is the ratio of the mass of a soil to the mass of an equal volume of water. For coarse-grained soils, 1000 millimeter density bottle gas jar may be used, but for fine-grained soils, a special conical-topped glass jar called a pycnometer should be used. The procedure to determine particle density is very important, and it should be noted that the range of particle density of common soil particles is very narrow, typically 2.6 2.7 milligram per minus cubic meter. Soil porosity, macropores and micropores. The size of the individual pore spaces rather than their combined volume will have the most effect on air and water movement in soil. Here you can see a macropore and micropore. This is a micropore and this is a macropore. Pores smaller than about 0.05 millimeter or finer than sand in diameter are typically called micropores. Pores larger than 0.05 millimeter are called macropores. Macropores allow the ready movement of air, roots, and percolating water. Micropores in most soils are typically filled with water, and this doesn't permit much air movement into or out of the soil. Soil-water relationships. Moisture content. The amount of water in a soil has a profound effect on its engineering properties. For example, under compaction, dry density varies with water content. This illustration shows how water content influences dry density. A soil compacted dry will reach a certain dry density. If compacted and again with the same compacted effort but with the water, a higher dry density will be reached. The water helps to lubricate the soil. The particles move closer on compaction. Also, air in the mixture is removed during the process. However, too much water reduces the density. Optimal moisture content occurs when the compacted dry density is at the maximum. Here you can see the optimum moisture content. A point to note is that optimum moisture content varies with the nature of the soil and compaction method. Heavy compaction plant produces a higher value of dry density at a lower optimum moisture content. To supply determine the moisture content of a soil. The following procedure can be followed. Record the mass of a dry container. Add the wet soil to the container and record the new mass. Container plus wet soil. Place the container, including the wet soil, in an oven at a temperature of around 100 degrees for about 24 hours. After the duration, record the mass of the container plus dry soil. The moisture content is then calculated from the following formula and is expressed as a percentage. Moisture content equals mass of water divided by mass of dry solid. Soil water holding capacity is determined largely by the interaction of soil texture, bulk density or pore space, and aggregation. Aggregation can be sands, clays, and clay soils. Sands hold little water because their large pore spaces allow water to drain freely from the soils. Clays absorb a relatively large amount of water and their small pore spaces retain it against gravitational forces. Clay soils hold water much more tightly than sandy soils. Soil drainage. Soil drainage is the rate and extent of vertical or horizontal water removal during the growing season. Important factors affecting soil drainage are slope or lack of slope, depth to the seasonal water table, texture of surface and subsoil layers, and of underlying materials. And of course, a very important factor is soil structure. Soil drainage indicators. Soil drainage is usually indicated by soil color patterns, such as spots and color variations with depth. Clear, bright red and yellow subsoil colors indicate well-drained conditions where iron and other compounds are present. Red and yellow subsoil, and this indicates well-drained condition. Subsoil zones with a mixture of bright red or yellow and gray spots. Here you can see many gray spots are indicative of seasonally fluctuating water tables, where the subsoil is wet during the winter or early spring and dry in the summer or early fall. Poorly drained soils tend to accumulate large amount of organic matter in their surface horizon because of limited oxidation and may have very thick and dark A horizons. Soil drainage class. The drainage class of a soil defines the frequency of soil weakness and is usually determined by the depth in soil of gray spots or other methods. Here you can see a depth to gray color. This is a well-drained soil. This is a moderately well, somewhat poorly, and this is a poorly drained because depths to gray color vary close. Soil survey. Now about soil survey reports. The soils of most countries have been mapped by the government soil survey program, and these maps are available in soil survey reports. Each soil survey report contains information about soil morphology, soil genesis, soil conservation, and soil productivity. Here you can see a soil scientist with map with information of morphology, soil genesis, and other. Soil survey reports. A soil survey report reveals the kinds of soils that exist in the country covered by the report at a level of detail for construction or agricultural purposes. The soils are described in terms of their location on the landscape, their profile characteristics, their relationships to one another. So this is a soil survey of Botwood County, Virginia. And parts of a soil surveys. Now we consider a soil maps and usually printed are an aerial photographic bus image. Each soil area is delineated by an enclosing line on the map. Soil delineation boundaries are drawn wherever there is a significant change in the type of soil. This is a portion of soil map from soil survey of Botwood County, Virginia.